Okay, so you know those numbers that kind of define our universe?
Mm-hmm. Like the speed of light, gravity, the big ones.
Exactly, the fundamental rules that
Yeah.
feel, well, fixed, right?
Immutable, yeah. Set in stone.
But what if, and this is a pretty big what if, there's a whole new set, new constants just waiting out there?
Constants describing things maybe way beyond what we currently measure.
Yeah, like hidden dimensions, or maybe the very essence of order, information flow, even life itself.
That's pretty much the core idea we're looking at today.
So that's our mission for this deep dive. We're going to unpack this really uh, groundbreaking document. It's titled New Universal Constants.
And it proposes exactly that. And it's not just pie in the sky thinking either.
Right.
Our source lays out a pretty detailed framework for these constants. It's got key equations, predictions you can actually test.
Testable predictions. Okay.
Yeah, and even potential experimental setup. So we're going to give you a kind of shortcut to understanding these ideas.
Highlighting the big insights.
Exactly, the most important points and, some surprising facts that could genuinely reshape how we see reality.
Okay, let's dive in then. So this source material, it introduces a whole bunch of new constants.
A dazzling array, as you said.
Yeah, dazzling is the word. But they seem to fall into two main buckets, right? Hyperspace and coherence. Could you sort of lay out what those mean here?
Sure, so first, hyperspace. In this context, it's talking about higher dimensional spaces.
More than our usual 3 dimensions of space or 4 space-time.
Precisely, dimensions beyond those. And these hyperspace constants, they're basically tools to formally model how physics might work if you extend it into those realms.
Okay, modeling physics in extra dimensions, got it. And coherence.
Then there's coherence. Now, this is a really key concept in the paper. It's about order, it's about synchronization.
How systems kind of hold together.
Exactly. How they maintain integrity, how they show structured growth, especially when faced with chaos or randomness.
So the opposite of entropy, basically.
Yeah, pretty much. Think of it like systems evolving towards greater order and certainty. The source actually calls this negentropy.
Negentropy, okay.
And what's really interesting here is the attempt to actually quantify these kinds of emergent organizational properties.
Which seems incredibly difficult. How do you put a number on order?
Well, that's what these coherence constants aim to do. It's a big conceptual leap.
It really is. So, okay, if we're talking higher dimensions, let's dig into those hyperspace constants first. This sounds like where things get really wild.
It does push the boundaries.
Let's start with the fundamental one mentioned, the hyperdimensional gravity constant, Chi. What's this telling us about gravity beyond our usual understanding?
Right, so G, this constant proposes a way to measure how gravity itself might change its behavior if you consider extraspatial dimensions.
Change how? Stronger, weaker?
It could be either or behave differently depending on the scale. But the key insight, I think, is that it suggests a mechanism for how effects from these unseen dimensions might actually influence our familiar 3D world.
Like bleeding through.
Kind of, yeah. Gravitational fingerprints from higher dimensions showing up here. It's even suggested this could potentially offer explanations for things we currently call dark matter or dark energy.
Wow, okay. That's a big claim.
It's a testable hypothesis, though. That's the important part.
All right, moving on. The hyperdimensional entanglement constant, Chi. Now, quantum entanglement? That's weird enough in 3D space.
It certainly is. Spooky action at a distance.
But the source suggests something kind of counterintuitive here. An inverse relationship with dimensionality.
That's right. Chi governs how entanglement works in these higher dimensional spaces. It might involve, extra degrees of freedom.
Okay.
But the really fascinating part is the proposed value. It might be inversely proportional to the dimensionality. So like 1n, where n is the number of dimensions.
Wait, so more dimensions could mean less entanglement?
Potentially, yes. Lower entanglement entropy. And think about the implications, say, for quantum computing.
Right. Entanglement is key, but also delicate.
Yeah.
Decoherence is a huge problem.
Exactly. So if you could simulate or somehow access circuits operating in, say, a 4D or 5D space, well, this lower entanglement might lead to more stable qubits, less decoherence.
That would be revolutionary for quantum computing.
It's a very different angle on tackling that challenge, yeah. A testable prediction, too, for advanced quantum experiments.
Amazing. Okay, what about time? There's a hyperspace time dilation constant, GHTD. That sounds like it's taking relativity into these extra dimensions.
Essentially, yes. It defines the relationship between how time is perceived or flows in a hyperspace continuum versus our normal four-dimensional space-time.
So it modifies Einstein's time dilation.
It suggests an additional factor, yeah, a hyperspace contribution. Time might behave differently depending on interactions with these hyperspace structures, maybe different speeds of time or different flows connected to higher dimensions.
Mind-bending stuff. Let's try and ground this a bit. There's also the hyperfractal quantum interface constant, HQ. That sounds incredibly complex, fractals and quantum particles.
It does sound complex, but it leads to a concrete experimental idea. This constant, HQ, governs how quantum behavior changes when particles interact with fractal shapes.
Fractal geometries, like coastlines or snowflakes.
Exactly, shapes with self-similarity at different scales. But here, the source suggests actually building one in the lab, like a Sierpinski gasket lattice.
Build a fractal. How?
Using optical lattices, basically, grids made of laser light or atomic traps, which use magnetic fields. You can arrange atoms in these incredibly precise, complex patterns.
Okay.
So you create this fractal environment, and then you study quantum particles moving within it. You look for deviations in their energy levels, or how easily they tunnel, or how long they stay coherent.
And those deviations would tell you something about this HQ constant.
That's the proposal. You could estimate the constant based on those measurements and the fractal dimension of your lattice. It's about seeing how fundamental quantum rules meet extreme geometric complexity.
That's a really clever experimental design. Okay, so that's hyperspace. But you mentioned the other big category was coherence. What does this framework say about order and organization in the universe?
Right, the coherence constants. This shifts the focus from dimensions to, well, how things organize and synchronize.
From tiny cells to the whole cosmos.
That's the scope, yes. The framework basically posits that coherence isn't just something that happens sometimes. It might be a fundamental organizing principle.
A universal principle of order. Let's start with the hyperinformation negentropy constant, Churatia. You mentioned negentropy earlier, systems moving towards order. How does that fit with, well, everything we know about entropy?
It's a challenge to the standard view, for sure. Shuane essentially describes the potential for information, possibly in hyperspace, to actively organize itself.
So instead of just disorder increasing, like entropy dictates.
Exactly. This proposes a kind of counterflow towards greater order, greater certainty. The constant quantifies how well-defined or organized information states can become. It suggests a fundamental tendency towards self-organization.
That idea feels almost biological. Which leads us to constants like the cellular coherence constant, CCC, and the neural coherence constant, CNC. How do these apply to us?
Yeah.
To living systems?
Very directly. The cellular coherence constant, CCC, focuses on how cells within tissues or networks coordinate their activities.
Like talking to each other.
In a way, yes. Synchronizing to maintain balance, homeostasis, respond to signals, manage immune responses, even things like tissue repair. It's about cells working together harmoniously.
And the neural one, CAC.
Similar idea, but for the brain. CAC governs the coherence of neural networks, how different brain regions synchronize their electrical activity to let us do complex things.
Like paying attention, remembering things, making decisions.
Exactly. All those rely on coordinated, coherent brain activity. These constants propose a way to quantify that underlying biological coordination.
It's fascinating to think there might be fundamental numbers behind that kind of biological complexity.
Yeah.
Now, what about the coherence transition constant, CAC? That sounds like a tipping point.
It is. It describes a threshold where a system can suddenly sort of snap into a coherent state.
Can we actually see that happen? Is there a real-world example?
Oh, absolutely. The source gives a great example. Superconductors.
Ah, where electricity flows with zero resistance.
Right. Take a high-temperature superconductor, like YBCO, that's yttrium, barium, copper oxide. Above a certain temperature, it's just a regular ceramic. But cool it below its critical point, around 90 Kelvin.
Which is still pretty cold, but high for a superconductor.
Right. Below that specific temperature, bang, it sharply transitions into this highly coherent superconducting state. Electrons pair up and move in perfect synchrony. C-less defines that critical threshold where coherence abruptly emerges.
Okay, that makes it very concrete.
Yeah.
And the last coherence one here is the multimodal coherence constant, CMC. Sounds like it connects different types of coherence.
Precisely. It quantifies how different modes of coherence might interact or enhance each other. Think quantum coherence, like in superposition interacting with, say, electromagnetic coherence, like synchronized light waves, or even thermal coherence.
So they don't just exist side by side, they can influence each other.
That's the idea. The source suggests looking at systems like a superconducting qubit, a building block for a quantum computer coupled to an electromagnetic cavity, like in cavity QED experiment.
Where you trap light and matter together.
Exactly. In a hybrid system like that, the total coherence you observe might be way stronger than just adding up the individual coherences of the qubit and the cavity.
Like a synergistic effect.
Yes, a strong multimodal interaction. And CMC would be the constant that scales that interaction strength.
Okay, so we have these incredibly abstract, yet maybe profound concepts: hyperspace, coherence, negentropy. But how on earth do scientists even begin to test these constants? It feels like a huge jump from theory to experiment.
It's definitely a challenge, but the framework really leans into empirical testability. That's crucial.
So it's not just math on paper.
No, the source actually details specific predictions and potential experimental setups across a lot of fields too: quantum optics, particle physics, condensed matter physics, like the superconductor example, even cosmology.
You mentioned the fractal lattice for Chayefsky.
Right, that's one example. Observing quantum particles in those engineered fractal environments, that's a concrete, albeit difficult, experiment.
But, hang on. If these effects, especially the hyperspace ones, are real, but maybe incredibly subtle, wouldn't they be drowned out by noise? How could we ever measure something potentially minuscule?
That's a really important question. And this is where the document introduces another fascinating idea: amplification mechanisms.
Amplification, like
Yeah.
turning up the volume on these tiny effects.
Sort of, yeah. The idea is that certain conditions or systems could naturally amplify these very small fundamental effects, making them observable, leading to what the source calls disproportionately large effects.
Okay, how would that work? What kind of mechanisms are we talking about?
Well, the source highlights a few main types. First, resonance effects.
Like you mentioned with the swing analogy earlier.
Exactly. If a system is operating near a specific resonant frequency, even a very weak, tiny nudge or interaction, if it's at that frequency, can build up and be amplified many, many times.
Makes sense. What else?
Second, nonlinear dynamics. Many systems in nature, especially complex ones like biological systems, don't follow simple linear rules.
Right, small changes can have unpredictable, large consequences. The butterfly effect idea.
Precisely. In these nonlinear systems, a tiny perturbation, maybe from one of these new constants, could be magnified into large-scale observable changes.
And the third amplifier.
Feedback loops. Particularly positive feedback, where an initial small effect triggers a response that further increases the effect, which triggers more response.
The snowball effect again.
Yeah. A tiny initial signal gets fed back and amplified, potentially leading to huge outcomes. Think microphone squeal, but applied to fundamental physics or biology.
Wow. So the universe might have built-in amplifiers for these subtle effects. Can you give a really concrete example from the source of how this amplification would make a constant testable?
Sure. Let's take the negentropy coherence hyperspace interaction constant, CNCHS. That sounds complicated, but bear with me.
Okay.
The source suggests testing this using Bose-Einstein condensates, or BECs.
Those ultra-cold atoms that act like one single quantum wave.
Exactly. They are incredibly sensitive systems. Now, imagine you carefully tune a BEC so it's near a resonance condition. According to the source, even a tiny influence from hyperspace related to negentropy may be quantified as just 10 to 4 or 10 to 5 joules per Kelvin, incredibly small.
Practically nothing.
Right. But because of the resonance amplification in the BEC, this tiny influence could lead to measurable shifts in how long the BEC stays coherent, or the precise temperature at which it forms.
So the BEC acts like a massive antenna and amplifier for this tiny effect.
That's the concept. It makes something otherwise invisible visible.
Give me one more, maybe biological.
Okay, consider the biological organization constant, CNLHS. This relates to those nonlinear dynamics and feedback loops we talked about.
Right, inherent in living systems.
Yes. Think about gene regulation networks. Metabolic pathways are full of feedback. The source suggests that a minuscule hyperspace interaction may be related to coherence, again on the order of 10 to 5 something, could be amplified by these inherent biological dynamics into significant observable changes. Things like an organism's growth rate, maybe its lifespan, or its ability to adapt to stress.
That implies a really deep connection between fundamental physics, these constants, and life itself.
It really does. A potential link between the cosmos and biology at a very fundamental level.
So pulling this all together, these ideas about coherence, order, negentropy, especially with these amplification mechanisms, where does it leave us? The source mentions a unified framework for coherence.
Indeed. It's proposing that coherence isn't just a random property that pops up here and there. It's suggesting coherence might be a universal principle.
Underpinning everything.
Underpinning order, synchronization, alignment across all scales.
Right.
From quantum systems staying entangled,
To cells working together using CCC.
to brains thinking via CNC.
And even huge structures in the cosmos.
Potentially, yes. Maintaining alignment over billions of years. This unified framework suggests there's a deep, fundamental order to the universe, governed by these coherence principles that we're really only just starting to grasp how to quantify.
And maybe even influence eventually.
Perhaps. That's looking far ahead, but quantifying is the first step.
We've really gone on a journey here into a vision of reality where, well, everything from the tiniest quantum flicker to the largest structures in space might follow a new set of rules, these new universal constants.
Constants that try to bridge physics with concepts like higher dimensions, yes, but also information, order, even life.
It suggests a much more interconnected and perhaps inherently organized cosmos than we often think about.
Absolutely. This framework really pushes us to think beyond our familiar four dimensions and to seriously consider how fundamental order and information might be to the way the universe actually works. Not just side effects, but core components.
Which leaves a pretty big question for you, the listener, to chew on.
What if these constants aren't just describing reality as it is? What if they're actively shaping it, driving the emergence of complexity, structure, maybe even consciousness itself?
That's a powerful thought. This whole deep dive just shows how dramatically our picture of the universe could change. It really invites you to think, okay, if coherence is a fundamental universal principle, what does that open up?
What new possibilities for quantum computing stability, for understanding biology, maybe healing, regeneration?
Or even for searching the cosmos, looking for signs of this inherent order, or maybe even large-scale intelligence structure in a new light. Lots to think about.